In this video, I'd like to start talking about a second type of unsupervised learning problem called dimensionality reduction. There are a couple different reasons why one might want to do dimensionality reduction. One is data compression, and as we'll see later, a few videos later, data compression not only allows us to compress the data and have it therefore use up less computer memory or disk space, but it will also allow us to speed up our learning algorithms. But first, let's start by talking about what is dimensionality reduction. As a motivating example, let's say that we've collected a dataset with many features, and I've plotted just two of them here. And let's say that unknown to us, two of the features were actually the length of something in centimeters, and a different feature, x2, is the length of the same thing in inches. So this gives us a highly redundant representation, and maybe instead of having two separate features, x1 and x2, both of which basically measure the length, maybe what we want to do is reduce the data to one-dimensional and just have one number measuring its length. In case this example seems a bit contrived, this centimeter and inches example is actually not that unrealistic and not that different from things that I see happening in industry. If you have hundreds or thousands of features, it's often just easy to lose track of exactly what features you have. And sometimes you may have a few different engineering teams. Maybe one engineering team gives you 200 features, the second engineering team gives you another 300 features, and the third engineering team gives you 500 features. So you have 1,000 features altogether, and it actually becomes hard to keep track of exactly which features you got from which team, and it's actually not that hard to have highly redundant features like these. And so if the length in centimeters was rounded off to the nearest centimeter and length in inches was rounded off to the nearest inch, then that's why these examples don't lie perfectly on a straight line, because of round off error to the nearest centimeter or the nearest inch. And if we can reduce the data to one dimension instead of two dimensions, that reduces the redundancy. For a different example, again, maybe one that seems slightly less contrived, for many years I've been working with autonomous helicopter pilots, or I've been working with pilots that fly helicopters. And so if you were to measure, if you were to do a survey or do a test of these different pilots, you might have one feature, x1, which is maybe the skill of these helicopter pilots, and maybe x2 could be the pilot enjoyment, that is, how much they enjoy flying, and maybe these two features will be highly correlated. And what you really care about might be this sort of this direction, a different feature that really measures pilot aptitude. And I'm making up the name aptitude, of course, but again, if you have highly correlated features, maybe you really want to reduce the dimension. So let me say a little bit more about what it really means to reduce the dimension of the data from two dimensions, that is from 2D to one-dimensional or to 1D. Let me color in these examples slightly different colors. And in this case, by reducing the dimension, what I mean is that I would like to find maybe this line, this direction on which most of the data seems to lie, and project all the data onto that line that I just drew. And by doing so, what I can do is just measure the position of each of the examples on that line, and what I can do is come up with a new feature, z1, and to specify the position on the line, I need only one number. So z1 is a new feature that specifies the location of each of those points on this green line. And what this means is that whereas previously, if I had an example x1, maybe this was my first example, x1, so in order to represent x1, originally x1, I needed a two-dimensional number, or a two-dimensional feature vector. Instead, now I can represent z1. I can use just z1 to represent my first example, and that's going to be a real number. And similarly, x2, if x2 is my second example there, then previously, whereas this required two numbers to represent, if I instead compute the projection of that black cross onto the line, and now I need only one row number, which is z2, to represent the location of this point z2 on the line, and so on through my m examples. So just to summarize, if we allow ourselves to approximate the original data set by projecting all of my original examples onto this green line over here, then I need only one number, I need only one row number to specify the position of a point on a line. And so what I can do is therefore use just one number to represent the location of each of my training examples after they've been projected onto that green line. So this is an approximation to the original training set because I have projected all of my training examples onto a line. But now I need to keep around only one number for each of my examples. And so this halves the memory requirement or the disk space requirement or what have you for how to store my data. And perhaps more interestingly, more importantly, what we'll see later in the later video as well is that this will allow us to make our learning algorithms run more quickly as well. And that is actually perhaps even the more interesting application of this data compression rather than reducing the memory or disk space requirement for storing the data. On the previous slide, we showed an example of reducing data from 2D to 1D. On this slide, I'm going to show another example of reducing data from 3-dimensional or 3D to 2-dimensional 2D. By the way, in a more typical example of dimensionality reduction, we might have 1,000-dimensional data or 1,000D data that we might want to reduce to, let's say, 100-dimensional, 100D. But because of the limitations of what I can plot on the slide, I'm going to use examples of 3D to 2D or 2D to 1D. So let's say I have a data set like that shown here, and so I would have a set of examples, xi, which are points in R3, so 3-dimensional examples. I know it might be a little bit hard to see this on the slide, but I'll show a 3D point cloud in a little bit. And it might be hard to see here, but maybe all of this data maybe lies roughly on the plane, like so. And so what we can do with dimensionality reduction is take all of this data and project the data down onto a 2-dimensional plane. So here what I've done is I've taken all the data and I've projected all of the data so that it all lies on the plane. Now finally, in order to specify the location of a point within a plane, we need two numbers, right? We need to maybe specify the location of a point along this axis and then also specify its location along that axis. So we need two numbers, maybe called z1 and z2, to specify the location of a point within a plane. And so what that means is that we can now represent each example, each training example, using two numbers that I've drawn here, z1 and z2. So our data can be represented using vectors z, which are in R2. And these subscripts, z subscript 1, z subscript 2, what I just mean by that is that my vectors here, z, are 2-dimensional vectors, z1, z2. And so if I have some particular example, zi, well, that's a 2-dimensional vector, zi1, zi2. And on the previous slide, when I was reducing data to 1-dimensional data, then I had only z1, right? But and that's what the z1 subscript on the previous slide was. But here I have 2-dimensional data, so I have z1 and z2 as the two components of the data. Now, let me just make sure that these figures make sense. So let me just re-show these exact three figures again, but with 3D plots. So the process we went through was that shown in the left is the original dataset, in the middle the dataset projected onto 2D, and on the right the 2D dataset with Z1 and Z2 as the axes. Let's look at it a little bit further. Here's my original dataset, shown on the left, and so I had started off with a 3D point cloud like so. So where the axes are labeled x1, x2, x3, and so this is a 3D point cloud, but most of the data maybe roughly lies on, not too far from some 2D plane. So what we can do is take this data, and here's my middle figure. I'm going to project it onto 2D. So I've projected this data so that all of it now lies on this 2D surface. Okay, you can see all the data lies on a plane because I projected everything onto a plane. And so what this means is that now I need only two numbers, z1 and z2, to represent the location of a point on the plane. And so that's the process that we can go through to reduce our data from 3-dimensional to 2-dimensional. So that's dimensionality reduction and how we can use it to compress our data. As we'll see later, this will allow us to make some of our learning algorithms run much later as well, but we'll get to that only in a later video. In the last video, we talked about dimensionality reduction for the purpose of compressing the data. In this video, I'd like to tell you about a second application of dimensionality reduction, and that is to visualize the data. For a lot of machine learning applications, it really helps us to develop effective learning algorithms if we can understand our data better, if we have some way of visualizing the data better. And so dimensionality reduction offers us often another useful tool to do so. Let's start with an example. Let's say we've collected a large data set of many statistics and facts about different countries around the world. So maybe the first feature, X1, is the country's GDP, or the gross domestic product. X2 is the per capita, meaning the per person GDP. X3, Human Development Index, life expectancy. X5, X6, and so on. And we may have a huge data set like this with, maybe 50 features for every country, and we may have a huge set of countries. So is there something that we can do to try to understand our data better? So given this huge table of numbers, how do you visualize this data? If you have 50 features, it's very difficult to plot 50-dimensional data. So what is a good way to examine this data? Using dimensionality reduction, what we can do is, instead of having each country represented by this feature vector xi, which is 50-dimensional, so instead of, say, having a country like Canada, instead of having 50 numbers to represent the features of Canada, let's say we can come up with a different feature representation that is these z vectors that is in R2. If that's the case, if we can have just a pair of numbers, z1 and z2, that somehow summarizes my 50 numbers, maybe what we can do is then plot these countries in R2 and use that to try to understand the space and these sorts of features of different countries a little bit better. And so here, what you can do is reduce the data from 50 dimensions to 2D, so we can plot this as a two-dimensional plot. And when you do that, it turns out that if you look at the output of the dimensionality reduction algorithms, it usually doesn't ascribe a particular meaning to these new features z1 and z2. And it's often up to us to figure out, roughly what these features means. But if you plot what these features, here's what you might find. So here, every country is represented by a point zi, which is in R2. And so each of those dots in this figure represents a country. And so here's z1 and here's z2. And highlight a couple of these. So we might find, for example, that the horizontal axis, the z1 axis, corresponds roughly, to the overall country size, or the overall economic activity of a country. So the overall GDP, overall economic size of a country. Whereas the vertical axis in our data might correspond to the per person GDP, or the per person well-being, or the per person economic activity. And you might find that given these 50 features, these are really the two main dimensions of variation. And so out here, you might have a country like the USA, which is a relatively large GDP, it's a very large GDP, and a relatively high per person GDP as well. Whereas here, you might have a country like Singapore, which actually has a very high per person GDP as well, but because Singapore is a much smaller country, the overall economy size of Singapore is much smaller than the US. And over here, you would have countries where individuals are sort of unfortunately somewhat less well off, maybe shorter life expectancy, less healthcare, less economic activity, as well as smaller countries. Whereas a point like this would correspond to a country that has a substantial amount of economic activity, but where individuals tend to be somewhat less well off. But so you might find that the axes z1 and z2 can help you to more succinctly capture really what are the two main dimensions of variations amongst different countries. such as the overall economic activity of a country, reflected by the size of the country's overall economy, as well as the per person individual well-being measured by per person GDP, per person healthcare, and things like that. So that's how you can use dimensionality reduction in order to reduce data from 50 dimensions or whatever down to 2 dimensions or maybe down to 3 dimensions so that you can plot it and understand your data better. In the next video, we'll start to develop a specific algorithm called PCA, or Principal Components Analysis, which will allow us to do this and also do the earlier application I talked about of compressing the data. For the problem of dimensionality reduction, by far the most popular, by far the most commonly used algorithm is something called Principal Components Analysis, or PCA. In this video, I'd like to start talking about the problem formulation for PCA. In other words, let's try to formulate precisely exactly what we would like PCA to do. Let's say we have a data set like this. So this is a data set of examples X in R2, and let's say I want to reduce the dimension of the data from 2-dimensional to 1-dimensional. In other words, I would like to find a line onto which to project the data. So what seems like a good line onto which to project the data? It seems like a line like this might be a pretty good choice. And the reason we think this might be a good choice is that if you look at where the projected versions of the points go. So I'm going to take this point and project it down here and get that. This point gets projected here, to here, to here, to here. What we find is that the distance between each point and the projected version is pretty small. That is, these blue line segments are pretty short. So what PCA does formally is it tries to find a lower dimensional surface, really a line in this case, onto which to project the data so that the sum of squares of these little blue line segments is minimized. The length of those blue line segments, that's sometimes also called the projection error. And so what PCA does is it tries to find the surface onto which to project the data so as to minimize that. As an aside, before applying PCA, it's standard practice to first perform mean normalization and feature scaling so that the features x1 and x2 should have 0 mean and should have comparable ranges of values. I've already done this for this example, but I'll come back to this later and talk more about feature scaling and mean normalization in the context of PCA later. But coming back to this example, in contrast to the red line that I just drew, here's a different line onto which I could project my data, which is this magenta line. And as you can see, this magenta line is a much worse direction onto which to project my data, right? So if I were to project my data onto the magenta line, I get a set of points like that. And the projection errors, that is these blue line segments, would be huge. So these points have to move a huge distance in order to get onto the get projected onto the magenta line. And so that's why PCA, Principal Components Analysis, would choose something like the red line rather than like the magenta line down here. Let's write out the PCA problem a little more formally. The goal of PCA, if we want to reduce data from 2-dimensional to 1-dimensional, is we're going to try to find a vector that is a vector ui, which is going to be an Rn, so that would be an R2 in this case. I'm going to find the direction onto which to project the data so to minimize the projection error. So in this example, I'm hoping that PCA will find this vector, which I'm going to call U1, so that when I project the data onto the line that I define by extending out this vector, I end up with pretty small reconstruction errors, end up with sort of data that looks like this. And by the way, I should mention that whether PCA gives me U1 or negative U1 doesn't matter. So if it gives me a positive vector in this direction, that's fine. If it gives me sort of the opposite vector facing in the opposite direction, so that would be like minus U1, let's draw that in blue instead. Right? Whether it gives me positive U1 or negative U1, it doesn't matter because each of these vectors defines the same red line onto which I'm projecting my data. So this is a case of reducing data from 2-dimensional to 1-dimensional. In the more general case, we have n-dimensional data and we want to reduce it to k dimensions. In that case, we want to find not just a single vector onto which to project the data, but we want to find k dimensions onto which to project the data so as to minimize this projection error. So here's an example. If I have a 3D point cloud like this, then maybe what I want to do is find vectors. So find a pair of vectors, and I'm going to call these vectors, let's draw these in red. I'm going to find a pair of vectors, so starting from the origin, here's u1, and here's my second vector, u2, and together these two vectors define a plane, or they define a 2D surface, right? Kind of like this sort of 2D surface onto which I'm going to project my data. For those of you that are familiar with linear algebra, for those of you that are really experts in linear algebra, the formal definition of this is that we're going to find, a set of vectors, u1, u2, maybe up to uk, and what we're going to do is project the data onto the linear subspace spanned by this set of k vectors. But if you're not familiar with linear algebra, just think of it as finding k directions instead of just one direction onto which to project the data. So finding a k-dimensional surface, really finding a 2D plane in this case, shown in this figure, where we can define the position of a point in the plane using k directions. And that's why for PCA we want to find k vectors onto which to project the data. And so more formally, in PCA, what we want to do is find this way to project the data so as to minimize the sort of projection distance, which is the distance between the points and the projections. And so in this 3D example too, given a point, we would take the point and project it onto this 2D surface. We end up with that. And so the projection error would be, the distance between the point and where it gets projected down to my 2D surface. And so what PCA does is it'll try to find a line or a plane or whatever onto which to project the data to try to minimize that squared projection, that 90-degree or that orthogonal projection error. Finally, one question I sometimes get asked is, how does PCA relate to linear regression? Because when explaining PCA, I sometimes end up drawing diagrams like these, and that looks a little bit like linear regression. It turns out PCA is not linear regression, and despite some cosmetic similarity, these are actually totally different algorithms. If we were doing linear regression, what we would do would be, on the left, we would be trying to predict the value of some variable y given some input features x. And so linear regression, what we're doing is we're fitting a straight line so as to minimize the squared error between point and this straight line. And so what we'd be minimizing would be the squared magnitude of these blue lines. And notice I'm drawing these blue lines vertically, right? That these blue lines are the vertical distance between the point and the value predicted by the hypothesis. Whereas in contrast, in PCA, what it does is it tries to minimize the magnitude of these blue lines, which are drawn at an angle. These are really the shortest orthogonal distances, the shortest distance between the point x and this red line. And this gives very different effects depending on the data set. And more generally, when you're doing linear regression, there is this distinguished variable y that we're trying to predict. That all that linear regression is about is taking all the values of x and trying to use that to predict y. Whereas in PCA, there is no distinguished, or there is no special variable y that we're trying to predict, and instead we have a list of features, x1, x2, and so on up to xn, and all of these features are treated equally. So no one of them is special. As one last example, if I have three-dimensional data and I want to reduce data from 3D to 2D, so maybe I want to find two directions, u1 and u2, onto which to project my data, then what I have is I have three features, x1, x2, x3, and all of these are treated alike. All of these are treated so symmetrically, and there's no special variable y that I'm trying to predict. And so PCA is not linear regression, and and even though at some cosmetic level they might look related, these are actually very different algorithms. So hopefully you now understand what PCA is doing. It's trying to find a lower dimensional surface onto which to project the data so as to minimize this squared projection error, to minimize the squared distance between each point and the location of where it gets projected. In the next video, we'll start to talk about how to actually find this lower dimensional surface onto which to project the data. In this video, I'd like to tell you about the principal components analysis algorithm. And by the end of this video, you know how to implement PCA for yourself and use it to reduce the dimension of your data. Before applying PCA, there's a data pre-processing step which you should always take. Given a training set of m unlabeled examples, it's important to always perform mean normalization, and then depending on your data, maybe perform feature scaling as well. So this is very similar to the mean normalization and feature scaling process that we had for supervised learning. In fact, it's actually exactly the same procedure, except that we're doing it now to our unlabeled data x1 through xm. So for mean normalization, we first compute the mean of each feature, and then we replace each feature x with x minus its mean. And so this makes each feature now have exactly 0 mean. And then second, if the different features have very different scales. So for example, if x1 is the size of the house and x2 is the number of bedrooms, to use our earlier example, we then also scale each feature to have a comparable range of values. And so similar to what we had with supervised learning, we would take I subscript j, that's the j feature, and so we would subtract off the mean, now that's what we have on top, and then divide by Sj. Here Sj is some measure of the range of values of feature j, so it could be the max minus min value, or more commonly it is the standard deviation of feature j. Having done this sort of data pre-processing, here's what the PCA algorithm does. We saw from the previous video that what PCA does is it tries to find a lower dimensional subspace onto which to project the data so as to minimize these squared projection errors. The sum of the square projection errors is the square of the length of those blue line segments. And so what we wanted to do specifically is find a vector u1 which specifies that direction, or in the 2D case we wanted to find two vectors u1 and u2 to define this surface onto which to project our data. So just as a quick reminder of what reducing the dimension of the data means, for this example on the left, we were given examples xi, which are in R2, and what we like to do is find a set of numbers zi in R with which to represent our data, right? So that's what reduction from 2D to 1D means. And so specifically, by projecting the data onto this red line there, we need only one number to specify the position of a point on the line. So I'm going to call that number z, or z1. Z here, this is a row number, so that's like a one-dimensional vector. So z1 just refers to the first component of this, one by one matrix, right? This one-dimensional vector. And so we need only one number to specify the position of a point. So if this example here was my example x1, then maybe that gets mapped here, and if this example was x2, maybe that example gets mapped here, and so this point here would be z1, and this point here would be z2, and similarly, we would have those other points for these maybe x3, x4, x5 get mapped to z1, z2, z3. So what PCA has to do is we need to come up with a way to compute two things. One is to compute these vectors, u1, and in this case u1 and u2, and the other is how do we compute these numbers z. So on the example on the left, we're reducing the data from 2D to 1D. In the example on the right, we would be reducing data from 3-dimensional, so xi is in R3, to zi, which is now 2-dimensional. So these z vectors would now be 2-dimensional, so it would be z1, z2 like so, and so we need to give a way to compute these new representations, the z1 and z2 of the data as well. So how do we compute all of these quantities? It turns out that a mathematical derivation, or sort of a mathematical proof for what is the right value for u1, u2, z1, z2, and so on, that mathematical proof is very complicated and beyond the scope of the course. But once you've done all that math derivation, it turns out that the procedure to actually find the value of u1 that you want is not that hard, even though the mathematical proof that this value is the correct value is somewhat more involved and more than I want to get into. But let me just describe the specific procedure that you have to implement in order to compute all of these things, the vectors u1, u2, and these vectors z. Here's the procedure. Let's say we want to reduce the data from n-dimensional to k-dimensional. What we're going to do is first compute something called the covariance matrix. And the covariance matrix is commonly denoted by this Greek alphabet, which is the capital Greek alphabet sigma. It's a bit unfortunate that the Greek alphabet sigma looks exactly like the summation symbol. So this is the Greek alphabet sigma. It's used to denote a matrix, and this here is a summation symbol. So hopefully in these slides there won't be ambiguity about which is sigma, the matrix, the covariance matrix, and which is a summation symbol. And hopefully it'll be clear from context, when I'm using each one. Having computed this matrix sigma, and let's say we were to store it in an octave variable called sigma, what we need to do is then compute something called the eigenvectors of the matrix sigma. And in octave, the way you do that is you use this command, usv equals svd of sigma. SVD, by the way, stands for singular value decomposition. This is much more advanced singular value decomposition. This is much more advanced linear algebra than you actually need to know, but it turns out that when sigma is a covariance matrix, there are a few ways to compute these eigenvectors, and if you're an expert in linear algebra and if you've heard of eigenvectors before, you may know that there's another octave function called eig, which can also be used to compute the same thing. And it turns out that the SVD function and the I function will give you the same eigenvectors, only SVD is a little bit more numerically stable. So I tend to use SVD, although I have a few friends that use the I function to do this as well. But when you apply this to covariance matrix sigma, they'll give you the same thing. That's because the covariance matrix always satisfies a mathematical property called symmetric positive semi-definite. You really don't need to know what that means, but the SVD and the I functions are different functions, but when they're applied to a covariance matrix, which can be proved to always satisfy this sort of a mathematical property, they'll always give you the same thing. Okay, that was probably much more linear algebra than you needed to know. In case none of that made sense, don't worry about it. All you need to know is that this is a command you should implement in Octave. And if you're implementing this in a different language than Octave or MATLAB, what you should do is find a numerical linear algebra library that can compute the SVD or singular value decomposition. And there are many such libraries, for probably all the major programming languages, and you should be able to use that to find a routine to compute the matrices U, S, and V given of the covariance matrix sigma. So just to fill in some more details, this covariance matrix sigma will be an n by n matrix. And one way to see that is if you look at the definition, this is an n by 1 vector, and this here, xi transpose, is 1 by n, and so the product of these two things is going to be an n by n matrix. Right, so this 1 by n is xi transpose 1 by 1 is 1 by n, so that's a n by n matrix, and when you add up a bunch of these, you still have an n by n matrix. And what the SVD outputs is three matrices, U, S, and V. And the thing we really need out of the SVD is the U matrix. So the U matrix will be also an n by n matrix. And if we look at the columns of the U matrix, it turns out that the columns of the U matrix will be exactly those vectors, U1, U2, and so on, that we want. So U will be an n by n matrix. And if we want to reduce the data from n dimensions down to k dimensions, then what we need to do is just take the first k vectors. And that will give us U1 up to UK, which are the k directions onto which we want to project the data. So to describe the rest of the procedure from this SVD numerical linear algebra routine, we get this matrix U, and I'm going to call its columns U1 through UN. So just to wrap up the description of the rest of the procedure, From the SVD numerical linear algebra routine, we get these matrices U, S, and D. And so here's the matrix U, and we're going to use the first k columns of this matrix to get U1 through UK. Now, the other thing we need to do is we need to come up with a way to take my original data set, X, which is in Rn, and find a lower dimensional representation, Z, which is in Rk for this data. So the way we're going to do that is I'm going to take the first k columns of the U matrix. So I'm going to construct this matrix. I'm going to stack up U1, U2, and so on up to UK in columns. It's really basically taking this part of the matrix, right? The first k columns of this matrix, and so this is going to be an n by k matrix. I'm going to give this matrix a name. I'm going to call this matrix U subscript reduce. It's sort of a reduced version of the U matrix, maybe. I'm going to use it to reduce the dimension of my data. And the way I'm going to compute Z is going to let Z be equal to this U reduced matrix transpose times X. Or alternatively, to write out what this transpose means, when I take the transpose of this U reduced matrix, what I'm going to end up with is these vectors now in rows. I have U1 transpose down to UK transpose, and then take that times X, and that's how I get my vector Z. Just to make sure that these dimensions make sense, this matrix here is going to be k by n, and X here is going to be n by 1, and so their product here will be k by 1, and so Z is k-dimensional, is a k-dimensional vector, which is exactly what we wanted. And of course, these x's here, right, can be examples in our training set, can be examples in our cross-validation set, can be examples in our test set. And for example, if I want to take training example I can write this as xi, and that's what will give me zi over there. So to summarize, here's the PCA algorithm on one slide. After mean normalization, it says ensure every feature has zero mean, and optionally feature scaling, which you really should do feature scaling if your features take on very different ranges of values. Because after this pre-processing, we compute the covariance matrix sigma, like so. And by the way, if your data is given as a matrix like this, if you have your data given in rows like this, if you have a matrix capital X, which is your entire training set written in rows, right, x1 transpose down to xm transpose, this covariance matrix sigma actually has a nice vectorized implementation, so that you can implement in Octave. You can implement sigma equals 1 over m times x, which is this matrix up here, transpose times x, and this simple expression, that's a vectorized implementation for how to compute the matrix sigma. I'm not going to prove that this is a correct vectorization, but if you want, you can either numerically test this out yourself by trying out an Octave and making sure that both this and this implementations give the same answers, or you can try to prove it yourself mathematically. Either way, but this is a correct vectorized implementation for how to compute sigma. Next, we can apply the SVD routine to get U, S, and D, and then we grab the first k columns of the U matrix to get U reduce, and finally this defines how we go from a feature vector X to this reduced dimension representation Z. And similar to k-means, if you're applying PCA, the way you'd apply this is with vectors X in Rn, right? So this is not done with the x0 equals 1 convention. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that this procedure actually gives the projection of the data onto the k-dimensional subspace, onto a k-dimensional surface that actually minimizes the square projection error. The mathematical proof of that is beyond the scope of this course, but fortunately the PCA algorithm can be implemented in not too many lines of Octave code, and if you implement this in Octave or MATLAB, you actually get a very effective dimensionality reduction algorithm. So that was the PCA algorithm. One thing I didn't do was give a mathematical proof that the U1, U2, and so on, and the Z's and so on that you get out of this procedure is really the choices that will minimize the squared projection error, right? Remember we said what PCA tries to do is it tries to find a surface or a line onto which to project the data so as to minimize that squared projection error. So I didn't prove that this actually achieves that, and the mathematical proof of that is beyond the scope of this course. But fortunately, the PCA algorithm can be implemented in not too many lines of octave code. And if you just implement this, this is actually what will work, or this will work well. And if you implement this algorithm, you get a very effective dimensionality reduction algorithm that does do the right thing of minimizing this squared projection error. In some of the earlier videos, I was talking about PCA as a compression algorithm, where you may have, say, 1,000 dimensional data and compress it to a 100-dimensional feature vector, or have 3-dimensional data and compress it to a 2-dimensional representation. So if this is a compression algorithm, there should be a way to go back from this compressed representation back to an approximation of your original high-dimensional data. So given Zi, which may be 100-dimensional, how do you go back to your original representation Xi, which was maybe 1,000-dimensional? In this video, I'd like to describe how to do that. In the PCA algorithm, we may have an example like this. So maybe that's my example X1, and maybe that's my example X2. And what we do is we take these examples and we project them onto this one-dimensional surface, and then now we need to use only a row number, say Z1, to specify the location of these points after they've been projected onto this one-dimensional surface. So given a point like this, given a point Z1, how can we go back to this original two-dimensional space? And in particular, given a point Z, which is in R, can we map this back to some approximate representation X in R2 of whatever the original value of the data was? So whereas Z equals U reduced transpose X, if you want to go in the opposite direction, the equation for that is we're going to write X approx equals U reduce times Z. And again, just to check the dimensions, here U reduce is going to be an n by k dimensional vector. Z is going to be a k by 1 dimensional vector. So when you multiply these out, that's going to be n by 1. And so X approx is going to be an n-dimensional vector. And so the intent of PCA, that is if the square projection error is not too big, is that this X approx will be close to whatever was the original value of X that you had used to derive Z in the first place. To show a picture of what this looks like, this is what it looks like. What you get back out of this procedure are points that lie on the projection of that onto the green line. So to take our early example, if we started off with this value of x1 and we got this value of z1, if you plug z1 through this formula to get x1 approx, then this point here, that would be x1 approx, which is going to be in R2, and so and similarly, if you do the same procedure, this would be x2 approx, and that's a pretty decent approximation to the original data. So that's how you go back from your low dimensional representation Z back to an uncompressed representation of the data. We get back an approximation to your original data X. And we also call this process reconstruction of the original data, where we think of trying to reconstruct the original value of X from the compressed representation. So, given an unlabeled data set, you now know how to apply PCA and take your high dimensional features X and map it to this lower dimensional representation Z. And from this video, hopefully you now also know how to take these low representations Z and map it back up to an approximation of your original high dimensional data. Now that you know how to implement and apply PCA, what I'd like to do next is talk about some of the mechanics of how to actually use PCA well. And in particular, in the next video, I'd like to talk about how to choose K, which is how to choose the dimension of this reduced representation vector Z. In the PCA algorithm, we take n-dimensional features and reduce them to some k-dimensional feature representation. This number K is a parameter of the PCA algorithm. This number k is also called the number of principal components, or the number of principal components that we retain. And in this video, I'd like to give you some guidelines, or sort of tell you about how people tend to think about how to choose this parameter k for PCA. In order to choose k, that is, to choose the number of principal components, here are a couple useful concepts. What PCA tries to do is it tries to minimize the average square projection error. So it tries to minimize this quantity, which I'm writing down, which is the difference between the original data x and the projected version x approx I, which was defined in the last video. So it tries to minimize the square distance between x and its projection onto that lower dimensional surface. So that's the average square projection error. Also, let me define the total variation in the data to be the average length squared of these examples xi. So the total variation in the data is, the average over my training set of the length of each of my training examples. And this sort of says, on average, how far are my training examples from the vector, from just being all zero. So how far is how far on average are my training examples from the origin. When we're trying to choose k, pretty common rule of thumb for choosing k is to choose the smallest value so that the ratio between these is less than 0.01. So in other words, pretty common way to think about how to choose k is we want the average square projection error, that is the average the distance between x and its projections, divided by the total variation of the data, that is how much the data varies. We want this ratio to be less than, let's say, 0.01, or to be less than 1%, which is another way of thinking about it. And the way most people think about choosing k is, rather than choosing k directly, the way most people talk about it is as what this number is, whether this is 0.01 or some other number. And if this is 0.01, another way to say this, to use the language of PCA, is that 99% of the variance is retained. I don't really want to, don't worry about what this phrase really means technically, but this phrase 99% of the variance retained just means that this quantity on the left is less than 0.01. And so if you are using PCA, and if you want to tell someone, how many principal components you retained, it'd be more common to say, well, I chose k so that 99% of the variance was retained. And that's kind of a useful thing to know. It means that, the average square projection error divided by the total variation, that was at most 1%. That's kind of an insightful thing to think about. Whereas if you tell someone that, well, I had 100 principal components, or k was equal to 100 in 1,000 dimensional data, it's sort of harder for people to interpret that. So this number 0.01 is what people often use. Other common values will be 0.05, and so this will be 5%. And if you do that, then you go and say, well, 95% of the variance was retained, and other numbers, maybe around 90% of the variance was retained, maybe as low as 85%. So that 90% would correspond to saying this to 0.10, and so kind of parents 10%. And so range of values from 90, 95, 99, maybe as low as 85% of the variance retained would be a fairly typical range of values. And maybe a 95 to 99 is really the most common range of values that people use. And for many data sets, you'd be surprised, in order to retain 99% of the variance, you can often reduce the dimension of the data significantly still, and still retain most of the variance, because for most real-life data sets, many features are just highly correlated, and so it turns out to be possible to compress the data a lot and still retain 99% of the variance, or 95% of the variance. So how do you implement this? Well, here's one algorithm that you might use. We might start off, if you want to choose the value of k, we might start off with k equals 1, and then we run through PCA. So we compute ureduce, compute z1, z2, up to zm, compute all those x1 approx and so on up to xm approx, and then we check if 99% of the variance is retained. Then we're good, and we'll use k equals 1, but if it isn't, then what we'll do is we'll next try k equals 2. And then we'll again run through this entire procedure and check, is this expression satisfied? Is this less than 0.01? And if not, then we do this again. Let's try k equals 3, then try k equals 4, and so on until maybe we get up to k equals 17 and we find that 99% of the variance is retained, and then we use k equals 17, right? So that's one way to choose choose the smallest value of k so that 99% of the variance is retained. But as you can imagine, this procedure seems horribly inefficient. If we're trying k equals 1, k equals 2, we're doing all these calculations. Fortunately, when you implement PCA, it actually, in a step, it actually gives us a quantity that makes it much easier to compute these things as well. Specifically, when you're calling SVD to get these matrices U, S, and V, when you're calling SVD on the covariance matrix sigma, it also gives us back this matrix S. And what S is going to be a square matrix, and n by n matrix, in fact, that is diagonal. So it's diagonal entries S11, S22, S33, down to SNN are going to be the only non-zero elements of this matrix, and everything off the diagonals is going to be 0. Okay, so those big O's that I'm drawing, by that what I mean is that everything off the diagonal of this matrix, all of those entries there are going to be zeros. And so what is possible to show, and I won't prove this here, but it turns out that for a given value of k, this quantity over here can be computed much more simply, and that quantity can be computed as 1 minus sum from I equals 1 through k of Sii divided by sum from I equals 1 through n of Sii. So just to say that in words, or just to take another view of how to explain that, if k equals 3, let's say, what we're going to do to compute the numerator is sum from I equals 1 through 3 of Sii, so we just compute the sum of these first 3 elements, so that's the numerator. And then for the denominator, well, that's the sum of all of these diagonal entries. And 1 minus the ratio of that gives me this quantity over here that I've circled in blue. And so what we can do is just test if this is less than or equal to 0.01, or equivalently, we can test if sum from I equals 1 through k, Sii divided by sum from I equals 1 through n, Sii, if this is greater than or equal to 0.99, if you want to make sure that 99% of the variance is retained. And so what you can do is just slowly increase k, set k equals 1, set k equals 2, set k equals 3, and so on, and just test this quantity to see what is the smallest value of k that ensures that 99% of the variance is retained. And if you do this, then you need to call the SVD function only once, because that gives you the S matrix, and once you have the S matrix, you can then just keep on doing this calculation by increasing the value of k in the numerator, and so you don't need to keep on calling SVD over and over again to test out different values of k. So this procedure is much more efficient, and this can allow you to select the value of k without needing to run PCA from scratch over and over. You just run SVD once. This gives you all of these diagonal numbers, all of these numbers, S11, S22, down to SNN, and then you can just, vary k in this expression to find the smallest value of k so that 99% of the variance is retained. So to summarize, the way that I often choose k when I'm using PCA for compression is I would call SVD once on the covariance matrix, and then I would use this formula and pick the smallest value of k for which this expression is satisfied. And by the way, even if you were to pick some different value of k, even if you were to pick the value of k manually, maybe I have 1,000 dimensional data and I just want to choose k equals 100, then if you want to explain to others what you just did, a good way to explain the performance of your implementation of PCA to them is actually to take this quantity and compute what this is, and that will tell you what was the percentage of variance retained. And if you report that number, then people that are familiar with PCA, or people can use this to try to get a good understanding of how well your 100-dimensional representation is approximating your original data set, because it's 99% of variance retained. That's really a measure of your square reconstruction error, that ratio being at most 0.01, and just gives people good intuitive sense of whether your implementation of PCA is finding a good approximation of your original data set. So hopefully that gives you an efficient procedure for choosing the number k, for choosing what dimension to reduce your data to. And if you apply PCA to very high dimensional data sets, to like 1,000 dimensional data, very often, just because data sets tend to have highly correlated features, this is just a property of most of the data sets you see, you often find that PCA will be able to retain 99% of the variance, or retain 95, 99, some high fraction of the variance, even while compressing the data by a very large factor. In an earlier video, I had said that PCA can be sometimes used to speed up the running time of a learning algorithm. In this video, I'd like to explain how to actually do that, and also say some, try to give some advice about how to apply PCA. Here's how you can use PCA to speed up a learning algorithm, and this supervised learning algorithm speedup is actually the most common use of that I personally make of PCA. Let's say you have a supervised learning problem. Notice this is a supervised learning problem with inputs x and labels y, and let's say that your examples xi are very high dimensional. So let's say xi are 10,000 dimensional feature vectors. One example of that would be if you were doing some computer vision problem where you have 100 by 100 images, and so if you have 100 by 100, that's 10,000 pixels, and so if xi are feature vectors that contain your 10,000 pixel intensity values, then you have 10,000 dimensional feature vectors. So with very high dimensional feature vectors like this, a learning algorithm can be slow, right? Just if you feed 10,000 dimensional feature vectors into logistic regression or a neural network or support vector machine or what have you, just because that's a lot of data, that's 10,000 numbers, it can make your learning algorithm run more slowly. Fortunately, with PCA, we'll be able to reduce the dimension of this data and so make our algorithms run more efficiently. Here's how you do that. We're going to first take our labeled training set and extract just the inputs. So we're just going to extract the x's and temporarily put aside the y's. So this will now give us an unlabeled training set. So that's x1 through xm, which are maybe there's a 10,000 dimensional data, 10,000 dimensional examples that we have. So just extract the input vectors x1 through xm. Then we're going to apply PCA, and this will give me a reduced dimension representation of the data. So instead of 10,000 dimensional feature vectors, I now have maybe 1,000 dimensional feature vectors. So that's like a 10x savings. So this gives me, if you will, a new training set. So whereas previously I might have had an example x1, y1, my first training input is now represented by z1, and so I'm going to have a new sort of training example which is z1 paired with y1, and similarly z2, y2, and so on up to zm, ym, because my training examples are now represented with this much lower dimensional representation z1, z2 up to zm. Finally, I can take this reduced dimension training set and feed it to a learning algorithm, maybe a neural network, maybe logistic regression, and I can learn a hypothesis H that takes as input these low dimensional representations Z and tries to make predictions. And so if I were using logistic regression, for example, I would train a hypothesis that outputs 1 over 1 plus e to the negative theta transpose Z, or theta transpose Z, that takes as input one of these Z vectors and tries to make a prediction. And finally, if you have a new example, maybe a new test example X, what you do is you would take your new test example X, map it through the same mapping that was found by PCA to get you your corresponding Z, and that Z then gets fed to this hypothesis, and this hypothesis then makes a prediction on your input X. One final note, what PCA does is it defines a mapping from X to Z. And this mapping from X to Z should be defined by running PCA only on the training set. And in particular, this mapping that PCA is learning, right, this mapping, what that does is it computes a set of parameters, right? It does the feature scaling and mean normalization, and is also computing this matrix U reduce. But all of these things, like U reduce, that's like a parameter that is learned by PCA, and we should be fitting our parameters only to our training set and not to our cross-validation or test sets. And so these things, the uReduce and so on, that should be obtained by running PCA only on your training set, and then having found uReduce, or having found the parameters for feature scaling, right? The mean normalization and scaling, the scale that you divide the features by to get them onto comparable scales. But having found all those parameters on the training set, you can then apply the same mapping to other examples that may be in your cross-validation set or in your test set. Okay, but so just to summarize, when you're running PCA, run your PCA only on the training set portion of your data, not the cross-validation set or the test set portion of your data, and that defines the mapping from X to Z, and you can then apply that mapping to your cross-validation set and your test set. And by the way, in this example, I talked about reducing the data from 10,000 dimensional to 1,000 dimensional. This is actually not that unrealistic. For many problems, we can actually reduce the dimensional data, by 5x, maybe by 10x, and still retain most of the variance. And we can do this with barely affecting the performance in terms of classification accuracy, let's say, barely affecting the classification accuracy of the learning algorithm. And by working with low dimensional data, our learning algorithm can often run much, much faster. To summarize, we've so far talked about the following applications of PCA. First is the compression application, where we might do so to reduce the memory or the disk space needed to store data. And we just talked about how to use this to speed up a learning algorithm. In these applications, in order to choose K, often we'll do so according to figuring out what is the percentage of variance retained. And so is for this learning algorithm speedup application, often will retain 99% of the variance. That would be a very typical choice for how to choose K. So that's how you choose K for these compression applications. Whereas for visualization applications, well, usually we know how to plot only two-dimensional data or three-dimensional data. And so for visualization applications, we would usually choose K equals 2 or K equals 3 because we can plot only 2D and 3D data sets. So that summarizes the main applications of PCA, as well as how to choose the value of K for these different applications. I should mention that there's one frequent misuse of PCA. And you sometimes hear about others doing this, hopefully not too often, but just want to mention this so that you know not to do it. And there's one bad use of PCA, which is to try to use it to prevent overfitting. Here's the reasoning. This is not a great way to use PCA, but here's the reasoning behind this method, which is, if we have xi, then maybe we'll have n features, but if we compress the data and use zi's instead, then that reduces the number of features to k, which could be much lower dimensional. And so if we have a much smaller number of features, if k is 1,000 and n is 10,000, then well, if we have only 1,000 dimensional data, maybe we're less likely to overfit than if we were using 10,000 dimensional data with like 1,000 features. And so some people think of PCA as a way to prevent overfitting. But just to emphasize, this is a bad application of PCA, and I do not recommend doing this. And it's not that this method works badly. If you were to use this method to reduce the dimensional data to try to prevent overfitting, it might actually work okay. But this just is not a good way to address overfitting. And instead, if you're worried about overfitting, there's a much better way to address it, to use regularization instead of using PCA to reduce the dimension of your data. And the reason is, if you think about how PCA works, it does not use the labels y, right? You're just looking at your inputs xi, and you're using that to find a lower dimensional approximation to your data. So what PCA does is it throws away some information. It throws away or reduces the dimension of your data without knowing what the values of y is. So this is probably okay. Using PCA this way is probably okay if, say, 99% of the variance retained, if you're keeping most of the variance, but it might also throw away some valuable information. And it turns out that if you're retaining 99% of the variance or 95% of the variance or whatever, it turns out that just using regularization will often give you at least as good a method for preventing overfitting, and regularization will often work better, because when you're applying linear regression regression or logistic regression or some other method with regularization, well, this minimization problem actually knows what the values of y are, and so is less likely to throw away some valuable information, whereas PCA doesn't make use of the labels and is more likely to throw away valuable information. So just summarize, it is a good use of PCA if your main motivation is to speed up your learning algorithm, but using PCA to prevent overfitting, that's not a good use of PCA, and using regularization instead is really what many people will recommend doing instead. Finally, one last misuse of PCA. So I should say PCA is a very useful algorithm. I often use it, for the compression or the visualization purposes, but what I sometimes see is also people sometimes use PCA where it shouldn't be. So here's a pretty common thing that I see, right? Which is if someone's designing a machine learning system, they may write down a plan like this. Let's design a learning system. Get a training set, and then what I'm going to do is run PCA, then train logistic regression, and then test on my test data. So often at the very start of a project, someone will just write out a project plan that says, let's do these 4 steps with PCA inside. Before writing out a project plan that incorporates PCA like this, one very good question to ask is, well, what if we were to just do the whole thing without using PCA? And often people do not consider this step before coming up with a complicated project plan and implementing PCA and so on. And so specifically, what I often advise people is, before you implement PCA, I would first suggest that do whatever it is, take whatever it is you want to do, and first consider doing it with your original raw data xi. And only if that doesn't do what you want, then implement PCA and consider using CI. So before using PCA, instead of reducing the dimension of the data, I would consider, well, let's ditch this PCA step, and I would consider, let's just train my learning algorithm on my original data. Let's just use my original raw inputs xi. And I would recommend, instead of putting PCA into the algorithm, just try doing whatever it is you're doing with the xi first. And only if you have a reason to believe that doesn't work. So only if your learning algorithm ends up running too slowly, or only if the memory requirement or the disk space requirement is too large, so you want to compress your representation. But only if using the xi doesn't work, only if you have evidence or a strong reason to believe that using the xi won't work, then implement PCA and consider using the compressed representation. Because what I do see is sometimes people start off with a project plan that incorporates PCA inside, and sometimes whatever they're doing would have worked just fine even without using PCA instead. So just consider that as an alternative as well before you go and spend a lot of time to implement PCA and figure out what K is and so on. So that's it for PCA. Despite these last sets of comments, PCA is an incredibly useful algorithm when you use it for the appropriate applications, and I actually use PCA pretty often, and for me, I use it mostly to speed up the running time of my learning algorithms, but I think almost just as common an application of PCA is to use it to compress data, to reduce the memory or disk space requirements, or to use it to visualize data. And PCA is one of the most commonly used and one of the most powerful unsupervised learning algorithms. And with what you've learned in these videos, I think hopefully you'll be able to implement PCA and use them to all of these purposes as well.